Welcome to G Fun Facts Online. Let's talk about gold. For thousands of years, we've seen it as a symbol of wealth, beauty, and permanence. It's the noble metal, famously inert and unchanging. But what if I told you that at the smallest scales imaginable, gold is none of those things? What if, when you shrink it down to just a handful of atoms, it stops behaving like a metal and starts acting like something from a science fiction novel? We're not talking about regular gold nanoparticles, those tiny specks that give stained glass its ruby red color. We're talking about something far more precise. A new class of material that is poised to change everything. Atomically precise gold clusters. These are not just tiny chunks of gold. They are quantum machines, where the addition or subtraction of a single atom can unlock completely new powers. This is the dawn of a new atomic era in nanoscience. In the world of these clusters, gold is no longer just a shiny metal. It becomes a catalyst, a medical marvel, and even a building block for quantum computers. For centuries, our control over gold nanoparticles was an approximation. We could make them small, but we always ended up with a mixture of different sizes. This meant their properties were just an average, a blurred-out picture. But scientists began to ask a revolutionary question. What if we could build gold particles with the same precision as a chemical molecule? What if we could define them with a specific formula, like all 25, meaning exactly 25 gold atoms, no more, no less? The answer to that question has launched a new field and unveiled the surprising power of gold. When a gold particle shrinks below 2 nanometers, something amazing happens. The familiar metallic properties fade away. The sea of electrons that makes gold conductive gets squeezed into discrete, quantized energy levels, just like the electrons in a single atom. This is called quantum confinement, and it's so profound that these clusters are better described as superatoms. They are complex molecular entities with a specific number of gold atoms in their core and a precise number of stabilizing molecules called ligands on their surface. This atomic precision is the secret to their extraordinary and often astonishing abilities. So today, we journey into the heart of quantum mechanics to see how scientists learn to control matter, atom by atom, and how they are using these golden superatoms to reshape our world. The ability to create these materials is a marvel of modern chemistry. The journey started in 1994 with what's known as the Brust-Shiffrin method, a clever way to make gold nanoparticles. While a breakthrough, it still produced a mix of sizes. The real quest was for atomic purity. A major advance came with a technique called size focusing. Imagine you have a chaotic collection of different sized clusters. You put them in a specific chemical environment, maybe with extra stabilizing ligands and a bit of heat. Under these conditions, the most stable, most energetically perfect clusters begin to grow at the expense of all the others. It's a kind of chemical natural selection, where only the magic number clusters, the most robust configurations, survive and multiply. This is how scientists can now produce large quantities of specific clusters, like the famous O25. But how do they know they've succeeded? How can they be sure they have exactly 25 gold atoms and not 24 or 26? This requires a suite of incredibly sophisticated tools. First, they use mass spectrometry. This is essentially a hyper-accurate scale for molecules, allowing scientists to weigh the clusters and confirm their exact molecular formula. Then, for the ultimate proof, they turn to X-ray crystallography. By growing a single, perfect crystal of these nanoclusters, they can bombard it with X-rays. The way the X-rays scatter allows them to create a complete, three-dimensional map of every single atom's position. This has revealed the intricate and often beautiful structures of these superatoms, like the icosahedral or 20-sided core of the Shu-25 cluster. These techniques don't just confirm success, they unveil a new set of rules for building matter from the bottom up. So what makes these, magic number clusters so special and stable? The answer lies in a fascinating concept called the superatom model. This model proposes that a whole collection of atoms in a cluster can act together as a single, giant atom. This superatom has its own set of electronic shells, just like a regular atom has shells for its electrons. And just as noble gas atoms like helium and neon are incredibly stable because they have perfectly filled electron shells, gold clusters are extra stable when their superatomic shells are filled. The number of electrons needed to fill these shells, numbers like 2, 8, 18, 34, and 58, are the so-called magic numbers. The iconic Au-25 cluster is the perfect example. In its most common form, it has a core of gold atoms that contribute electrons to these superatomic shells, while the stabilizing ligands on the surface help lock in the perfect number of electrons to achieve a stable configuration. This superatom model explains more than just stability. It explains their unique properties. The discrete energy levels in these superatomic shells are why these clusters interact with light in such a special way, completely different from larger gold nanoparticles. It also explains their geometry. Instead of the standard crystal structure of bulk gold, they often form highly symmetric shapes like icosahedra, because that's the most energy-efficient way to pack the atoms at such a small scale. The superatom concept is a powerful illustration of how, at the nanoscale, the rules of chemistry and physics can be rewritten, allowing collections of atoms to take on entirely new identities. These new identities give the gold clusters a dazzling array of superpowers. Perhaps the most striking is their optical behavior. As we said, they don't behave like normal gold. They don't have that characteristic shimmer caused by surface plasmons. Instead, when light hits them, electrons jump between their discrete, quantized energy levels, just like in a molecule. This results in an absorption spectrum with multiple, sharp peaks. But what's even cooler is what happens next. After absorbing light, these clusters can relax by emitting light of their own, a phenomenon called photoluminescence. They glow, and the color of that glow can be precisely tuned by changing the number of atoms in the cluster. O10 might glow one color, while O25 glows another. This tunability makes them incredibly powerful fluorescent probes for all sorts of applications. Their electronic properties are just as revolutionary. The discrete energy levels make them perfect candidates for next-generation electronics, specifically for a device called a single electron transistor, or SET. A SET is the ultimate switch. It can control the flow of electricity one single electron at a time. This could lead to computers that are orders of magnitude faster and more energy efficient than anything we have today. In a SET, the gold cluster acts as a tiny island, a quantum dot, that can hold a specific number of electrons. By applying a voltage, you can control whether an electron is allowed onto the island or not, effectively switching the current on and off. The challenge is making these devices work at room temperature, which requires the kind of atomic precision we're now achieving. But the ambition doesn't stop there. Recent research suggests these gold clusters could play a role in the ultimate computational frontier, quantum computing. Scientists have found that these superatoms can have tunable spin properties, mimicking the highly accurate systems used in quantum information science today, but with the potential to be far more scalable. By changing the ligands on the cluster's surface, they can manipulate its quantum state. While still in its early days, this opens a tantalizing new path to harnessing quantum mechanics for computation. These amazing properties aren't just confined to the lab. They are already being used to solve real-world problems in catalysis and medicine. For decades, gold was considered catalytically inert, a chemical bystander. But the discovery that gold nanoparticles could be potent catalysts sparked a gold rush in chemistry. Atomically precise clusters have taken this to a new level. We now know that catalytic activity is intensely size-dependent. For some reactions, a cluster with 25 atoms might be a superstar catalyst, while a cluster of 26 atoms is completely inactive. This atomic precision allows scientists to design highly efficient and selective catalysts for important reactions. For example, they are brilliant at selective oxidation, converting one chemical to another without creating unwanted byproducts. They are also highly active in oxidizing carbon monoxide to carbon dioxide, a critical reaction for pollution control and in fuel cells. By correlating a cluster's exact atomic structure with its performance, scientists can finally understand the fundamentals of catalysis at the molecular level, paving the way for the rational design of perfect catalysts. Perhaps the most exciting applications, however, are in medicine. The unique combination of small size, tunable fluorescence, and biocompatibility makes gold nanoclusters almost perfect agents for nanomedicine. Their ultra-small size allows them to slip through biological barriers and enter cells in ways larger particles can't. Their photoluminescence makes them excellent probes for bioimaging. By tuning their glow to the near-infrared spectrum, they can be used to see deep inside tissues with minimal background noise. You can attach a targeting molecule to them, and they will specifically light up cancer cells. They can also be used as tiny delivery trucks for targeted drug delivery. A drug can be attached to the cluster's surface, and the cluster can be designed to accumulate directly at a tumor site. This increases the drug's effectiveness while dramatically reducing side effects on healthy tissue. The ultimate goal is a concept called theranostics, therapy and diagnostics in one package. A gold nanocluster can be used to find and image a tumor. Then, once it's in place, you can shine a specific frequency of light on it, causing it to heat up and destroy the cancer cells through photothermal therapy, or to generate reactive oxygen species to kill them through photodynamic therapy. It's a single agent that can both see the disease and treat the disease. In vivo studies are already showing that by carefully tuning their size and surface chemistry, we can control how these clusters move through the body and how they are eventually cleared through the kidneys, which is a critical step for clinical use. The field of atomically precise gold nanoclusters is still young, but it is brimming with potential. Of course, challenges remain. Making a wide variety of these clusters in large, cost-effective quantities is still difficult. We need to ensure they are stable and robust enough for harsh industrial or biological environments, and for medical use, comprehensive studies on their long-term safety are absolutely essential before they can be used in humans. But the opportunities on the horizon are breathtaking. Imagine a future with next-generation catalysts that turn industrial waste into valuable products, or create pharmaceuticals with zero impurities. Imagine a future of personalized medicine, where smart nanobots seek out and destroy disease at the cellular level, or tiny sensors inside our bodies continuously monitor our health. And imagine the dawn of quantum technologies, powered by these golden superatoms, leading to an entirely new era of information technology. The surprising power of atomically precise gold clusters lies in their ability to bridge the gap between the familiar world of matter and the strange, powerful world of quantum mechanics. They are a testament to our growing ability to control our world at its most fundamental level. The golden age of nanotechnology is upon us, and it is being forged, quite literally, one atom at a time.